There we go, we're recording now. So today's lesson is going to be about the normal distribution. We've got a few things we're going to do today. Let me just show you on the blog what it says we're going to do today. We are going to introduce the concept of a normal distribution. We already kind of introduced it yesterday. And we'll start with a video. I'm not going to record us watching the video, so I'll pause this while we watch the video. And then people at home can just do it off the blog. And then we're going to do part one in the notes booklet. We might even get started into part two. We'll see how much time we have. And then we'll have some work time. If anybody has anything they're completely stuck on the practice booklet from yesterday, I could take maybe a question later. But I do want to get into the new stuff. The normal distribution is kind of the most important part of this chapter. I mean, let's face it, 5.1, you could have done that in grade 6 or 7. Mean, median, mode, and range. Big deal. So we use the big fancy calculator or the computer app to find them. But come on, mean, median, mode, and range you've been doing since junior high. Standard deviation was a new idea, but it's not really that tough an idea, right? All that standard deviation is basically comparing how spread apart the data is compared to its own mean. And we assign a number to that. Now, how we get that number is kind of complicated. It is kind of a complicated formula, right? You have to find the mean, then you have to take every single data point, subtract the mean from it, square it, and then add them all up, and then square root. Oh, then divide by how many numbers it is, and then square root. It's complicated. That's a complicated formula. Thank goodness we have technology that does most of the work for us. Now we have an even more complicated idea here. This is, I think, where the rubber hits the road. First of all, let's just quickly, let me just get a blank page here. Do I have a blank page? There, blank page. We saw in a video yesterday the concept of a density curve. So if I had a histogram, let me just make up a pretend histogram here. Histogram, histogram, histogram. This is quite the histogram I've got happening here. There we go, histogram. Pretend all those bars are the same width. How do you turn your histogram into a density curve? Well, you do it in two steps. First of all, you have to make it a relative histogram, a relative frequency histogram. What that means is, if this was, say, 4 units high, instead of this being 4 units high, you have to change it to what percent of the data it is. So if this was 4 units, and this was, I don't know, say 5 units, and this was 6 units, and this was 7 units, then this, okay, I'm going to say this is now 5.5 units, and this is, oh, why don't I just shrink this down a bit? I don't want to deal with halves, do you? So there it goes. So this is 5 units. So this is 4, this is 5, this is 6, this is 7, this is 5 again, and this is 4 again. So instead of it being units high, we say, all right, well, all together here, the data is 4 plus 5, which is 9, 9 plus 6 is 15, 15 plus 7 is 22, 22 plus 5 is 27, 27 plus 4 is 31. So there's 31 data points in this data set. And 4 out of 31, let's do a quick calculation on that. 4 divided by 31 is 12.9, or let's just round it to 13% of the data. So this bar actually becomes that high. It doesn't change its shape any. And then this bar, which is, it used to be 5 points, is 5/31 of the data. 5 divided by 31 is, this would be 0.16 of the data, right? And this bar here, which was 6 out of 31, well, that's pretty, 6 divided by 31 is 19% of the data. Or again, I like decimals better, 0.19 is how high this bar is. That's a 9. And then finally, 7 out of 31, 7 divided 31 is 23% of the data. So this bar jumps up to 0.23. And it doesn't change how high the bars are relative to each other, but the scale now never makes it all the way to 1. In fact, it's usually much less than 1, because 1 is how much all of these bars' area is if you add them together. That's what makes it a density chart. So I said there was 2 steps to making a density chart. There's the first. The second is, of course, you have to somehow draw a curve over this. Now, how do you draw a curve? Well, you could join all the midpoints together and then kind of curve through through that, something like that. Right, the midpoints of all the bars is what I was trying to hit in my clumsy handwriting. And of course, there's another name for what I just drew too. Remember we called that a frequency polygon? Where you just join, of course, frequency polygon, you don't make a curve, usually you just use a broken line and join all the midpoints of all of the bars. So you could do that. You could make a curve instead of a broken line graph, and it's basically a frequency polygon. But again, to make it a nice density curve, the other step 2, to turn a histogram into a density curve, is instead of saying, well, class 1 was this many units, class 2 was this many units, class 3 was this many units, what if you had infinite number of classes? You could have like an infinite number of classes along the bottom. You're not breaking it into 1, 2, 3, 4, 5 groups. You could break it into 20 groups or 30 groups or 80 groups or 1,000,000 groups. Depends on how much data you have, obviously. But this line along here becomes continuous instead of a bunch of groups. And that's what makes it a density curve. So that's all there is to it. Now, I said yesterday when I showed you the little video that introduced density curve, I'm never going to make you make a density curve, but we have to learn how to interpret them. In fact, thinking about it, making a density curve, making a curve where it's really a histogram, where all of these little bins are so small, they're practically infinitely small, yeah, good luck doing that by hand. This is something that technology was made to do. I mean, computers at their very beginning were designed to do the most important task they do is count and do math much, much faster than people can do by hand. So making a density curve is perfect for a computer to do. So that's the first thing, is do we remember what a density curve is? Okay, now for the normal distribution, to first of all get a kind of an understanding of it, we're going to watch a video. So I'm going to pause. Guys at home who might be watching this, revisiting the lesson, it's this video here on the blog, but I'm not going to watch us watch a video. I'd probably get a strike on YouTube for copyright infringement anyway, right? So I'll pause the video, and then we'll watch that video. Okay, so we just watched the video, and now we're going to summarize kind of what we saw in our notes. So go to the 5.4 part of the notes, and let's answer this question first here. What is the normal distribution? So the normal distribution is a graph of data in a histogram, I should say histogram slash density curve format, where 100% of the data is contained under a symmetrical, and we'll call this, we'll use the same words they do. It's called a bell curve. And it looks like the picture below in your notes there. And there's 4 properties that we need to remember for sure. Actually 5, I guess, because technically one of the properties is that all of the area is 100%. I've already got that one though. So let's see, what are the properties we have to remember? Well, the property number 1 is that, of course, the mean value is the middle of the curve. And then there's the 3 parts of the rule. 68% of the data is between plus or minus. Are you guys cool with that symbol, plus or minus? You've seen that in math before, right? Plus or minus 1 standard deviation of the mean. Plus or minus. You can just write a little plus with a minus under it. "95% of the data is between positive and negative plus or minus 2 standard deviations of the mean." And finally, almost all of it, 99.7% of the data, if it's normally distributed, is between plus or minus 3 standard deviations of the mean. I'll give you a sec to catch up to me there. Okay, so the diagram below this section of the notes is this guy right here. And that's the illustration. That's the shape of the curve. That's a normal curve. And again, what does this mean? This means that, say we did something like found the height of everybody in Manitoba. I suppose we should probably separate it by gender. So every male in Manitoba. The average mean is this line here. We'd calculate the standard deviation, of course using technology, because that'd be 1.7 million pieces of data. So thank goodness we have computers to calculate standard deviation. Could you imagine taking every single number, minusing the mean, squaring that, and then when you're done getting all those squares, add them up, divide by 1.7 million, and then square root the answer? That would take a very long time. All right, so anyway, there's my mean. My standard deviation, whatever it is here and here, plus to the mean. So say the mean was, I don't know, what did they say in the other video? It was like 5'10", and say that the standard deviation was 2 inches. So this is 6 feet tall right here, and then this would be 5'8" right there. 68% of the people are between that height and that height, because that's the way normal distribution works. And that probably sounds about right. I'm estimating, but that sounds about right. And then, of course, there's the people who are unusually short, right? This would be your 5'6" to 5'8" right here, people. And then there's people who are even more unusually short. And then, of course, you have people who, for some sort of genetic reason, are significantly more short than the average population person. And they'd fall in this little tiny bit. Think about it. This end here and this end here are not even 1%. They're only 0.3%. Remember the video we watched, Where's Yao Ming? 1 in 450 million people are as tall as Yao Ming. So he's probably not even 4 standard deviations. He might even be the 5th or the 6th standard deviation. He'd be way out there. Again, what's that as a decimal? What percent of the population is 1 over 450 million? Remember how to change fractions to percents? First, change it to a decimal. 1 divided by 450, 1, 2, 3, 4, 5, 6. And I get 0.0000000, 1, 2, 3, 4, 5, 6, 7, 8, and then a 2. Oh, and then I got to make it a percent, so that means I move the decimal 2 places over. So he'd be way over here somewhere.
So it's like 0.00000.
Exactly. Normally distributed things like height, like weight, like exam scores, things where most people score near the mean. Well, so we don't know the standard deviation though. Again, what's the standard? Okay, we're making this up, but let's say, so this was, what was it, 5'10" was here? So that would be 6 foot, 6'2", 6'4", and then it'd be 6'6". Now I think actually the standard deviation here is too small. According to this, less than, let's see, what would this be again? This would be 0.0 something. I think there's more people who are 6'6" than that. Everybody knows somebody that's 6'6". Nobody in this room right now, but, right? They're not that unusual. But by the time you get to 7 foot, what is he, 7'4"? Yeah, then you're very, very unusual. But you get the idea. That's how these graphs work, and that's how we're going to use them. So let's move on to an example. It has been determined that a particular data set is distributed normally. The data set has a mean of 20. So that means this value right here on the graph is 20. So if that value is 20 and the standard deviation is 5, that means this is 25, this is 30, this is 35. Counting the other way, this is 15, this is 10, and this is 5. So, let's answer some questions. Let's make this smaller so I can fit them all on here. There we go. What % of the data lies between 15 and 25? And that is according to our, I can just delete that here. According to our notes, that's, oops, no, 20, that's 68%. What % lies between 10 and 30? According to our rule, 95%. What % lies between 10 and 20? Okay, so hang on a sec. We know that from 10 to 30, oh, hang on a sec. That's a 25. Yeah, we know that from 10 to 30 is 95%. So this is half of that. So that's 47.5%. Half of 95, right? What fraction lies between 20 and 35? Well, hold on a sec. Between here and here, 1, 2, 3 this way, and 1, 2, 3 that way, we have 99.7%. So between 20 and 35, what is our fraction here? So yeah, so let's see. Okay, that's a good idea. We could do that too. If you don't like cutting these numbers in half altogether, we can cut them in half individually. If it's 68 between here and here, then this is 34 and this is 34, right? If it's 95 from here to here, and we've already got 68 of it, that makes this 13.5% and this 13.5%. And then if it's 99.7 between these two all together, we already have 95% of it. That makes this 2.35 and this one 2.35. In fact, the diagram above kind of shows us that. So, one more time, how much is it between 20 and 35? It'd be 34 plus 13.5 plus 2.35. So that'd be a 5 there, and 8 there, and 7, 8, 9, and so 49.85% between 20 and 35. And what % of this data is less than 20? Well, hang on a sec. Remember, how come this doesn't add up to 100%? Because remember, these things do keep going. Like they said in the video, this line will actually never quite touch the x-axis to infinity, theoretically, right? We could then go, what's the theoretical probability somebody will be born that's 11 feet tall when they grow up? Well, boy, we'd be a lot of standard deviations over. It'd be so low a probability that it'd be basically impossible. But it's never 0. So that means that when I say less than 20, I'm not just including this zone, and this zone. I'm also including all the little zones to infinity. So it's actually 50%.
Right, because
Because that's still going after that. Even this little bit that's after that is still there. Question? That's, okay, the question, and it's a good one. Does this apply to any question, even when where it's ridiculous to say that the line goes to infinity, like people's heights? Does that mean there's some probability that somebody will be born that's 30 feet tall? Well, physically, no. But theoretically, in terms of the way that the numbers work, yes. Your chemistry teacher talks about this all the time. It's physically impossible to be 0 Kelvin, but we work with that number all the time because it's a theoretical number. So there we go. Does that answer your question? Yeah. Question? Yeah. Okay, so example 2. The masses of 8, okay, I got to draw myself a curve now, and I'm not good at this. So here we go. Here's my x-axis. Why? Because I wanted you to sketch one. The question is, why didn't you just draw one for us? Why don't I do everything for you? Geez, we got to draw one here. Come on, here we go. Bell curve, bell curve, bell curve, going up, going up, going down, going down, going down, going down, going down, going down. Oh, I'm not too sorry about that one. That's not bad. That looks like a pretty symmetrical bell curve. All right. You're just tracing it from the other side of the page? Cheaters. All right, so there's mu. There's my mean. And what's the mean this time? The mean of these athletes is 55 kilograms. And the standard deviation is 5. So 1 standard deviation, you start to kind of go down the curve here. And try to make this symmetrical. This should be the same size on either one. So this would be 5 in either direction, right? The standard deviation is 5. So just like the last example, I'm counting by 5s along my axis here. So this is 60. And then my second standard deviation, where I'm going to there and there, that would be 65 and 45. And then my next standard deviation, now they're getting, these are all the same distance horizontally. At least they should be. Sorry if my drawing's not perfect. And there we go. That's probably enough. Okay, so once again, let's use our rule. 68% of the data falls between those 2 standard deviations there, so why don't we call that 34%, 34% on either side. 95 falls between those 2, so to get to 95, I need another 27%. So that's 13.5 here, 13.5 here. And then to get to 99.7, I need another 4.7%, roughly. So that's 2.35 and 2.35. And there we go. If you add all that up, that's 99.7% of the data. So now let's and then after that, very good. It'd be actually, if you do want the next one, very good, you're right. The rest of this is 0.15% of the data on either side. You are correct. Because there's 0.3 remaining, right? Of a percent. 0.3 of a percent. So this is very small. By the time you're at that 4th standard deviation in a normal distribution, you're talking about a very small amount of the population. I like to think that if we measured everything there was to measure about people, everybody has at least some category we could measure where they'd belong up here and down here. So let's see. For me, what would I be the highest at if we measured the population? I don't know. No. It's somebody very, very kind of you to say. That guy just got an A. Because he said intelligence. No, I'm sorry. I'm very firmly in here. I'm not that much smarter than the average bear. I'm sorry. But how about something along the lines of, I don't know, Monty Python trivia knowledge? I could probably recite most of their sketches. I'd be up here. I'd be very high compared to the rest of the population. I might be in that 4th standard deviation. Where would I be at the very bottom? Oh, I don't know. There's some things in this. Oh, my memory skills are getting pretty bad. I suppose way down here would be like your Alzheimer patients and stuff, but I'd definitely be low. My short-term memory especially is bad. I don't know what that is. I'm good at remembering things from 30 years ago, but forming new memories, I'm like that guy from, what was that movie? Memento? Is that the one? You ever seen that movie? I'm almost as bad as that guy. Like, it's like 2 seconds after I do something, I've forgotten what I did. It's terrible. I got to get better at that somehow. Anyway, I like to think that we all fall into the bell curve on everything somewhere. Everybody's got something that puts them at the high end. Everybody's got something that puts them at the low end. It's just the way it goes. Now, what percentage of female athletes are between 45 and 65? So between 45 and 65 added up, that's going to be, well, you could go back to the rule. That's the 60, isn't that the 68%? Oh, no, 45 to 65, sorry, that's the 95 rule. So it's 95% are between there and there, right, isn't it? Yeah. 68, 95, yeah. Between 45 and 65? Oh, wait a minute, isn't that the same thing? Oh, how many athletes? So how many? So it's 95% of, how many athletes do we have here? 800. Can we do this in our head? No, we better grab a calculator. 0.95 times 800, we probably could. 10% would be 80, so 5% would be 40. Take 40 away from 800, 760 athletes. What percentage of female athletes were greater than 65? So greater than 65 would, of course, be, okay, so hold on a sec. If you're greater than 65, it's 2.5, isn't it 2.5? 35 and 15 is 0.5. So that's 2.5%, but that's now careful. If you want to find 2.5% of a number, you change the percent to a decimal. I just made a mistake on purpose. What did I do wrong? That's 25%. You always move the decimal over twice. There you go. Remember that? And what was it again? 800 athletes? And let's see. 25% of 800, a quarter of 800, is 200. So 2.5% would be 20. So point, another decimal over, isn't that just 2 athletes? Or is it 2? Oh, no, 2. Oh, that's what I want. I want 2.5. Sorry. So 20. 20 athletes. No, 2. Sorry, I went too far. Again, I guess I should try. I have a calculator in my hand. Why didn't I just punch buttons? But okay. Tried to use my brain. All right, we have a question. Because that's everything this way. So this is 2.35, and that's everything else after that is 0.15%. So I added those two together and got 2.5. Question? Because I think the question was in the middle. The question was, how many is less than 20? 20 is the median, or the mean. It's both. It's the mean and the median in this data, right? So how many are less? Isn't that half the data? Yeah. Yeah. Okay, back to this question. What percentage of female athletes had masses less than 40 kilograms? About 0.15%. How many athletes is that? 0.0015 times 800. And that's actually, I believe, less than 1. 0.0015 times 800 is 1. Oh, no, it's actually just a little over 1. But I'd round that. How do you have 1.2 of an athlete? So I'd round that to 1. The actual decimal points comes out to be 1.2 when you do the calculation. But we're talking about numbers of people, so I would just round to the nearest person. Would be the smart way to do that. Okay, so there's that one. Now here's a more visual question. Determine the standard deviation for each of the following graphs. So if I know that 68% of the data is between 15.25 and 15.75, that means that I know that the middle here is my mean. So how do you find the middle between two numbers? You add them up and divide by 2. So 15.25 plus 15.75, divide by 2. means that we have a mean of 15.5. You probably could have just figured that out from the picture, but let's do the math, because sometimes the numbers are harder than that, like the next one. So 15.5 is the mean, so what's the standard deviation? Well, the standard deviation is 1 unit over, so what's 15.75 minus 15.5? So this is the mean, so that number is mu, and this number, which turns out to be 0.25, that number is the one we want. That's our standard deviation. And we'll assume this is a population, not a sample. And most of these are populations, so we'll use the sigma. All right, let's do that. Let's do them with the tougher numbers. Oh, I lost you?
Yes.
If you count backwards by 0.25, you get to here, which is 15.5. So the standard deviation is the distance from here to here, which is 0.25.
Oh, it's because it's that little spot, isn't it?
Right?
It's asking-
It's asking what the standard deviation is. What is the standard deviation? It's the distance from the mean to this first histogram bar, or density curve bar, right? Now, in the next one, isn't there 2 standard deviations to get to the 95%? So there's a standard deviation here and here. So first thing I need to figure out is, again, what's this mean? And I find it the same way. It's halfway between those two things. So I'm going to add 4.575 plus 5.075 and divide by 2. So I'm going to use my calculator so I don't goof it up. 4.575 plus 5.075 divided by 2, and I get 4.825. So that's my mean. And then there's some number that I add 2 of them to this, and I get to 5.075. I've told you before in this course, we don't do much algebra, but we have to do it sometimes. Let's use sigma, since that is our variable. That's what we're looking for. 4.825 plus 2 standard deviations equals 5.075. Does everybody get where I got that equation from?
No.
This mean here, I got a whole bunch of no's, people. I don't know if you heard that at home on the microphone. 4.825 is the mean. We just figured that out, right? It's halfway between those numbers. I add some number, sigma, and I get to this first standard deviation. I add another sigma, and now I get to this one, and I know this one. It's 5.075. So the mean plus 2 standard deviations is 5.075. What is that standard deviation? How do you solve? Come on. This is grade 7 or 8 algebra. I take away 4.825 from both sides of the equation first. And that's negative, or it's not negative. I don't know why I put a negative there. It's 0.25. And then what's the next step algebraically? Divide both sides by 2. How did I get that number? I subtracted this from both sides of the equation. And then divide both sides of the equation by 2. And I get 0.125. All right. There it is. I'm going to hand out a little worksheet, a little practice sheet that has questions like these ones on it. And then we'll let you work for a few minutes. And then we might even start kind of looking a little bit at the calculator stuff. And if we do, I'll turn the lesson video back on. But actually, you know what? I don't think I will. We're down to 20 minutes. We'll just let you work for 20 minutes. So we'll pick it up here tomorrow, and we'll start looking at how we do this stuff using our calculator. Because obviously, these are easy to calculate. It's like, oh, that's right on the standard deviation number. What if they're not right on the number? Like, how much would it be if I wanted 70%, not 68? For that, we're going to need technology to help us. So that's where we'll land tomorrow. So that's it for today's lesson.